Hello, so in this video I'm going to cover a little bit, I'm going to go over integration, but the way that I'm going to do it is before I learned calculus, I wanted to know what it was about. It was something that probably I really should have already learned and just hadn't, so I was curious about it, and I watched some videos and had some people explain it to me, and basically there's some nice explanations that you can get that are about 30 seconds to maybe 5 minutes long, 10 minutes max, that kind of just give calculus in a nutshell, and they're very helpful, but obviously there's a reason that universities often require 3 or 4 semesters worth of calculus, and because it goes a lot deeper than that. And so in this video, I hope to give what's still an overview, but at the same time a deeper overview, and I only want to focus on integration. Because the second reason for making this video is because I find that during my studies, I'm now on my last of the 4 calculus courses that I have to take. I find that sometimes I'm losing the forest for the trees, especially when it comes to integration, because integrals can get very difficult to solve, to calculate for the solution. So a lot of time is spent on calculating for the solution, and not as much time, I feel like, at least in my program, is spent on setting them up and conceptually understanding them. And so that's why I just kind of want to go over this, what will be an overview of integration, but I'm not going to focus at all on solving them. In fact, I'm going to use a calculator to solve the integrals that I set up, because I want to focus on the setup and the application. Okay. It won't stop. There we go. And all right, so let's say that we have this shape right here, and we want to calculate the area of this shape. Let's say that this is 2. This is a much bigger size pencil than I want. I guess I'll keep it. And this is 2. Actually, I don't want such a big pencil. So since this is a triangle, say this is a right triangle, we happen to know, probably most people watching this will know, the area equals 1/2 base times height. Base times height, which in this case is going to be 2 times 2, which is 4. 4 divided by 2 is 2. So the area equals 2. But let's say that we didn't know that formula and we wanted to approximate that formula. Well, one way that you could do that, let's say the only thing that you knew how to calculate the area of was a rectangle or a square. And let's say that we want to approximate the area of this triangle. So one way you could do it is to break it up into small squares and add up those squares, or I should say rectangles. So let's do that. And for illustrative purposes, I'm going to start with one that you obviously wouldn't use, and that's this. If we turn the whole thing into a giant square, then we'll do, space out just a little bit. If you would divide it into 2 rectangles like this. So you're going to have, yeah, I'll go over that after. Next, we'll divide it into 4 rectangles, and I think that's good enough to get the point across. Like so. And as you can see in the pictures, this extra amount here is area that we're going to calculate that's actually not part of our true area of our triangle. So this is like our overestimate. And you can kind of tell visually here that the more rectangles we divide our triangle into, the smaller this overestimate gets. But in case that's not clear enough, we can go ahead and calculate it out. So let's say that the size of our triangle, once again, is 2 by 2. So this is 2 and this is 2. And we know already that the area of this triangle, the true area, is 2. According to this first estimate, we have our estimated area as base times height, 2 times 2, so 4. Here we come up with an estimate of 4, which is a lot bigger than 2, so we way overestimated. Over here we come up with an estimate of this height is 2, this width is 1, and this width is 1 because we divided 2 in half. And it may not be so intuitive here. It will be more so when I switch it to lay it on a coordinate plane. This height right here is 1. So this first rectangle, which actually happens to be a square, has an area of 1 because it's 1 times 1. The second rectangle has an area of 1 times 2, which is 2. So our total estimated area is 3. Now you can see that the intuition was correct. We broke the triangle down into more rectangles, and our estimate got smaller, which in this case happens to be closer to the correct answer. Let's do the same thing, but break it down into 4 rectangles. This is 2. 2 divided by 4, each of these is 1/2. 1/2. 1/2. 1/2. 1/2. Once again, maybe it's not so intuitive right here, but if you were to lay this on the Cartesian plane, it would be more apparent that this right here could be represented by the line y equals x. So this height, the height, will be whatever the x value is at that point. And this, so the base here is 1/2, the height's 1/2. 1/2 times 1/2 is 1/4. The second point, we have 1, a distance of 1 on the bottom, times a height, sorry, the height is 1 at this point. The distance across the bottom is still 1/2. So 1/2 times 1 is 1/2, but I'm going to change that to 2/4 so that the addition becomes easier. Now for the last one, the total length here is 3/2. So this height is 3/2, but our actual width that we're dealing with in our rectangle is 1/2. So 3/2 times 1/2 is 3/4. 3/4. And this one, we know the height, it's 2. 2 times 1/2 is 1. So this is 1. This is going to be 3/4 plus 1/4 is 1. So 1 plus 1 is 2. 2 plus 2/4. So we have 2.5. So once again, this just at least affirms that that we're moving in the correct direction. That the more times we break it up, the smaller we're getting. Technically, from what I just did, you don't necessarily know whether you'll ever get below the number 2, or if you're approaching the number 2, or if you're going below the number 2. I think if you just try to visualize it, you'll see that what we're doing, so the process we're doing is Riemann sums, except I'm not doing the notation. I'm intentionally not doing the notation. I find it more harmful than helpful. But if we were to break this up really tiny by starting at the right and going down, you'll see that no matter how small we make our little slices here, our little slivers, we're always going to have something sticking over. We'll never have something going underneath the triangle, which is what you would need for it to be smaller. So always we will be over. So what that means is the more you break this down, the closer you get to the number 2. And what happens is if you break this down an infinite amount of times, you exactly reach the number of 2. So let's kind of do that again, but not quite so lengthy, with on the Cartesian plane, because I want to show how this relates to shapes that are not so obvious, which is the reason for calculus. If we wanted to do obvious shapes, we wouldn't need to do calculus, because we can easily memorize a formula for finding the area of a triangle. So once again, laying this out, and the triangle that I had, the top of it here is represented by the line y equals x. And that can be known pretty easily because the base length of it was 2, which would mean that if this is the base, this is the point 2, 0, and this is the point 0, 0. And the height, as I already said, was 2. That was given in the problem. And if this is a right triangle, and this is 2, and this is 2, we know that this line is y equals x. Technically, what we know is that this is the point 2, 2. Anyway, I don't want to belabor the point. I think it's pretty apparent. So we have this, right? And the process that we just did, where I said the end result is that you break it down into an infinite amount of slices. I like that word. This is how you write it. So the integral from a to b of f of x dx. And what this kind of means, and to fill in the actual numbers for our actual problem, this would be the integral from, well, the dx tells us that we're moving along the x-axis, that our slices are in going along the x-axis. So here's a slice, here's a slice, except they're supposed to be really, really tiny slices, but in order to make my sketch not such a mess that you can't tell what's going on, here's some slightly thicker slices. So our slices are traveling in this direction. So that's what the dx means. So our a and b, our starting point and our ending point, should also be traveling along that same axis. And when we do that, we can see we start at this position, which is x equals 0. And we end at this position, which is x equals 2. F of x is another name for y, and in this case y equals x. So we would put an x in here, and that x value, what that actually represents is the height when we form our little rectangles. So let me use a new color so I can just kind of write over top of this here. Let's say we broke it down into not quite so many rectangles, so it's not such a mess. Actually, let me grab a bigger, make real fat lines here so it's easier to see. So there's 1, just say I broke it down into 3, 2, 3. You can see that the height at whatever point is the value for x, the value for y at this x position. So here is a certain x position right here, and whatever the height of this will be whatever y equals when we plug in x. Same here, same here. So that's why we're putting an x right here. This will get a little more clear as I go on. The dx represents the tiny little slice. So what we actually have, what this notation is telling us, is dx represents infinitesimally small slices along the x-axis. The integral means that we're summing up an infinite amount of those infinitely small slices. The 0 and the 2 tell us our starting point and stopping point. And then the x here is telling us that we multiply that times x, which is the height at every point. And we know that when we multiply width times the height, it gives an area, and we're adding up all the little areas. I hope that was clear enough. I think it'll get clearer as I go through more examples. So as I already showed, because this is a triangle, because we already know the solution here is 2, and once again, I'm going to try to intentionally avoid actually solving these by hand, just because I want to just focus on the setup. But if you were to solve this by hand, you would also see that this, what I just wrote, is 2. And okay, so there's a simple example. Now let's do the same thing, but with an example that where you would actually need calculus to find the area. And here what I want to graph is y equals x minus 1 cubed plus x minus 1 squared. And the graph for that should look something like this, something like that. Once again, this is x and this is y. And we want to go from x equals 0, which actually this should go through the origin. So this is the point 0, 0, and this is the point 2, 0. This is our height at the end anyway. And what else do I need? And this is the 0.22, which you wouldn't necessarily know, but I know because I already kind of worked this out. I set up the problem first and then graphed it afterwards. So the graph that I want us to find is y equals x minus 1 cubed plus x minus 1 squared. And if we take the integral of this, what we're finding is this area under this curve. Once again, conceptually what we're doing is, so let me write this down as it the way it would be written down. So we have the integral from 0 to 2, going from x equals 0 to x equals 2, of f of x, which in this case is that whole thing, x minus 1 cubed plus x minus 1 squared dx. And what this is telling us is that we're taking these infinitesimally small slices along the x-axis, so like this, except they're infinitesimally small, and we're going to multiply the width of that slice, which is represented by dx, times the height of that slice, which is represented by this, which will give us the areas of the individual slices. Then we're going to add up all of those areas going from 0 to 2. And that in total will give us area. And as I mentioned, I want to use a calculator. So I happen to really like Symbolab. For what I'm actually doing right now, probably Wolfram Alpha could be better, because I think it's okay to show this on my page. Try to make it where it actually fits on the screen. Oh, where's my mouse? Symbolab. And probably right about there. So we want the integral from 0 to 2 of x minus 1 cubed plus x minus 1 squared dx. So the reason that I like Symbolab, and the reason that Wolfram Alpha might be better for this, is because Symbolab, as you can kind of see, I'm not going to go over it right now. If you want to check out their website, it's Symbolab. It should come up pretty easily when you just type in it for an integral calculator. I really like theirs for learning purposes because it breaks it down into steps, and they're more or less the steps that you would be learning in class. So you can actually use it as like a training tool. I really like that, and also it only gives exact answers. Wolfram Alpha might be better for something like this, because since Symbolab only gives exact answers, it comes across problems that it can't solve. And Wolfram Alpha uses, and maybe it uses other stuff, I don't remember exactly, but I know for sure that it does at least sometimes use estimation techniques, and so it won't be an exact answer, but it would be an estimation. In a real world problem, it may be better sometimes to just get an estimation. Anyway. So our answer here, as you can see, is 2/3. So this would have been very hard to calculate, well, without using calculus. It's actually not too bad. It's a little bit lengthy, but it's not actually challenging to work it out by hand. But like I said, I want to intentionally keep the video away from that. So using integration, we're able to find the area under this curve. Let's see what else we can do with integration. Okay. Oh, I guess one more thing that I wanted to show about this finding area under a curve. And once again, I'll go back to the simple shape of a triangle where integration isn't actually needed, but I think for explanatory purposes and for the purposes of seeing the forest, it's a little easier to use really simple examples. And what I wanted to show here is, so let's go back to the same thing that we just had, which was this line y equals x. But before I went from x equals 0 to x equals 2, let's go from x equals -2 to x equals 0. So now what we're finding is this area right here. And if you were to do this, integral from -2 to 0 of x dx, either solving it by hand or plugging it into a calculator, what you'll find is that the solution to this is -2. So I just kind of wanted to show that when you use integration, you're actually finding the signed area. So what that means is, if you just straight up use integration to figure out, say this is y equals x again, and this is x equals -2, and now this is x equals 2. If you're finding the area of both of these together using integration, what you're going to find is that the solution is actually 0. So the integral from -2 to 2 of x dx equals 0. And the reason is because this is a -2 and this is a +2. You add them together, you get 0. So if you actually wanted to find the total area of this, not thinking of it as net area, but thinking of it as total area, you could either manipulate the line and move it all above the x-axis, or you could find the absolute value of this integral and then add it to the absolute value of this integral. So there's something to keep in mind. I think that's important conceptually. All right. Okay, what do I have next? The next thing, this was, once again, this is kind of just the next thing that's covered, and maybe I'll give it a title this time here. This is going to be areas between curves. So once again, we'll start with something really simple. So this is the x-axis, this is the y-axis, and we have two curves, which happen to be straight lines in this case, for simplicity's sake. This is y equals 2, and this is y equals 4. And this is going to be x equals 2. And this is going to be, not quite drawn to scale, x equals 4. And what we want to find, let's say we want to find this area in the center here. So Obviously, we can just calculate this in our heads because we know 4 minus 2 is 2. So this length is 2, and 4 minus 2 is 2. This length is 2. 2 times 2 is 4. So we already know, because this was a very simple example, that the area needs to equal 4. But let's see if we can use calculus to find this so that we can do the same thing with more complicated curves. So one thing that we can do is what we already know from the last example is if we find the area from just the area under the curve y equals 4, we know how to do that, and let's say that's this right here. Then we can kind of see visually that if we subtract away from that the area underneath it, underneath y equals 2, this area down here, what that will leave us with is the area inside here that we want. So that is the technique used to find the area between two curves. And if we were to set this up, kind of just if you like to see things in general terms, that would be the integral from a to b of f of x minus g of x dx. And yeah, so in this case, to set up this integral, we would have the integral from 2 to 4 of f of x is 4 minus g of x is 2. So as I kind of showed, we're taking the bigger one and subtracting away the smaller one. We're taking away the one that's farther from the x-axis and subtracting away the one that's closer to the x-axis. dx, which if you solve this by hand or plug this into a calculator, you'll see that the answer is 4. And just doing this mentally in my head, we get, yeah, which is 4. So that is how you can set up an integral to find the area between two curves. And one nice thing about this is you may have noticed, thinking about the last set of examples, we always had to go between a curve and the x-axis, so we always had to have at least one straight line. Most of the time you'd end up with 3 straight lines because you'd have the left side, the right side, and the bottom, and only the top would be curvy shaped. If you really got fancy, you could make the top just one giant curve so that only the bottom is flat. But this way we can end up with the whole thing curved, or at least easily the top and the bottom curved while the sides are flat. So let's look at another example. This is x, this is y, and here I want my curves to be, try to sketch these somewhat correct. That one, these go on forever, of course, I just didn't, like that. So this upper one I want to be 1/4 x squared, y equals 1/4 x squared. And the bottom one I want to be y equals 1 over x. And this time we'll go from x equals 2 to x equals 4. And if we find the area of the upper one to the x-axis and subtract away the area from the lower one to the x-axis, then we will end up with this area in the center, which is what we're trying to find. So to set that up, we're going to have the integral from 2 to 4 of f of x needs to be the one that's farther away from the x-axis, which for all of this, it is 1/4 x squared minus the one that's closer to the x-axis, which is 1 over x, dx. And we can plug this into a calculator. And once again, just as a reminder, conceptually what this is doing, this is breaking this up into thin slices along the x-axis, calculating the area of each little slice, and then summing up all of those slices. And let's go back to the calculator. I tested these out ahead of time. I tried to get ones that the calculator could solve, but I don't remember exactly how I typed this one in. So let's see if it gets it first try. 2 to 4, 1 over x minus 1 over 4x squared. So negative 14 over, natural log of 2 minus negative 14 over 3, or negative 3.97. We'll go with that. It shouldn't be negative. You know what? I think I did that last time too. Yeah, my bad. I just typed it in wrong. So I have 1/4 x squared minus 1 over x. Minus 1 over x. Should be the same, but with the opposite sign. So 3 point, whatever that was, 97, I think. Yeah, we'll go with that. 3.97. That is the area between these two curves. And that's very not intuitive, and that would be really difficult to calculate without calculus. And technically, yeah, I mean, you could use Riemann sums. I don't know if you're kind of using calculus at that point anyway, but especially if you take the limits to infinity. But at any rate, I think this demonstrates the usefulness for finding areas. And let's move on to the next thing. Okay, what's the next example? Okay, we're going to move from areas to volume, and there's actually there's a bunch of different ways to calculate volume, both ways that are learned in Calc 2 and ways that are learned in Calc 3. So let's take, how should I start this? Let's say that we have this sphere. Well, that's terrible. Let me try again. Yeah. Yeah, that's not so bad. Okay, so we have this sphere, and let's put it on the Cartesian plane, just because it's a little easier to work with. And let me go ahead and make it look a little bit more like a sphere by drawing like the, what would you call that? Like the equator at the center here, center point, and a little radius going out to the edge. Now, if we put this on the Cartesian plane, I'll go ahead and make that a different color. Like this. Now, so this is what we have. We have this sphere, And for this one, I think we're actually going to end up just coming up with the generic formula, because I have another video where I did this too. I happen to really like doing this. Let's say that we take, so conceptually what we're going to do, I'll grab another color here. We're going to be finding these little thin slices like this, where every thin slice is, let's think, if that's a sphere, these thin slices should be circles. It doesn't look like a circle, but this should be a perfect circle, and we would, create an infinitely many of them, and we're going to go along the x-axis again. You could do the y-axis, but for simplicity's sake in my video, I'm pretty much just going to stick with the x-axis. Not really any different going to the y-axis, but there's also no benefit in doing it for this video. So yeah, we're going to find the areas of all of these little circles running along this x-axis and add up all of the areas, and that will end up giving us the volume. So what we do though is going to be a little bit different, and I'm going to explain this a little bit different than I did in my other video. Let's say that we take, let me draw beside it. So let's say we just have this 2D shape like this, which is supposed to be the top half of a circle. So this is supposed to be perfectly circular. The equation of this is, well, if it was the whole circle, it would be y squared plus x squared equals r squared. But we just have half of the circle, and we actually want it in terms of y equals anyway, so this would be the equation y equals the square root of r squared minus x squared. And because we're not dealing with the negative half of the square root, we're only going to be dealing with this positive half of this circle. And conceptually then what we can do, the reason that I'm going through this is because this is kind of the way that you think about it when you do something that's not a circle anyway. In my other video I explained it a little bit different conceptually, but I think this is a better way to explain it. If you were to take this line, but not only this line, this area in between the line and the x-axis, if we were to take that area and rotate that area around the x-axis, it would end up forming the shape of a sphere. I think that's pretty easy to visualize. And so what we can do then is we can use this, well, you don't have to memorize it as a formula, but just I'm going to present it as a formula at this point. So the integral from a to b of the area with respect to x, I guess how you say that, with respect to x, dx. And this will give us the volume. And so what we're doing is the volume equals, if we have an area and we multiply it by a height, or in this case, since we're moving from left to right, we would have a slice that's going to look like, oops, that's so bad. Hold on, let me try again. Okay, it's going to look like this. There we go. All right, so we have this slice. It's a circle. It should be a circle since this is a sphere. And the radius of this slice goes from here to any outer point on the circle. So we can think of it as going from here to here. Would be the most convenient place to extend the radius to. When we take those, which have, to find the volume of this slice, we're going to take the area times the thickness. And in this case, we want the thickness to be dx. just like when we did finding the area under a curve, the thickness, the base of the rectangle was dx. In this case, the thickness of the circle, well, not circle, cylinder, of the super thin cylinder, the thickness is dx. So area times dx, this is actually volume. This formula is giving us a volume of the thin slices, and the integral is telling us to add up infinitely many of those infinitesimally small slices together, going from A, which is here, to B, which is here. So what's the area of this circle? The area, since this is a circle, we know it's a circle because its total shape is a sphere, and I think if you just play with it conceptually, you'll realize that whenever you slice a sphere perfectly perpendicular, I guess, you end up with circles. We're not slicing it a slant, we're slicing it perfectly perpendicular. Like, yeah. So area equals pi r squared. So we have area equals pi r squared, and in this case, as I kind of showed visually, r is going to be the height of the line at this point in the curve. Well, height is just y value, the y value. This is the y value at every point on this curve. So what we actually have is pi y squared, or pi f of x squared, and y equals this, square root of r squared minus x squared. So plugging in some real values, or almost real values, because I'm still going to use the r's, we're going from, this is the radius of the sphere, so this is negative r to positive r. Negative r to positive r of this area, which, as I already showed, is the square root of r squared minus x squared squared dx, which is going to be the area of the face of the circle times dx to give it a little bit of width and turn it into a cylinder. And this one, actually, I think you can use, can you use the calculator? Oh wait, I forgot to multiply by times pi. So pi r squared, so there's a pi there. And we should be able to, let me check, I actually think we can do this in the calculator. I think this will handle variables. Negative r to r of, and I'm going to move the pi out on the outside just because I like to. Pi, and it was r squared minus x squared. R squared minus x squared. All right. That should be correct. We'll have to do a little bit of, so it's got pi times 2r cubed pi times 2r cubed minus 2r cubed over 3, 2r cubed over 3. This is 6 over 3. 6 minus 2 is 4, so 4 over 3. We can then insert the pi, and we're left with r cubed. And you can look this up, or maybe you have it memorized. 4/3 pi r cubed is the formula for volume of a sphere. So there's one way to calculate volume, and when you're learning this would be called the disk method. There's another very similar method that's conceptually it's basically the same, called the washer method. I don't think they should have had two names for them. For me, it was more confusing than helpful. But and what else is there? Disk washer. There's a third one, I think. I forget the name of it right now. So let's just do one more of these. And what was the reason that I wanted to do this? Actually, I don't think there's any reason to do. Yeah, there's no reason to do the other one. So what do I have next? Let's take a cone. Let me just get this page cleaned up here. All right, so once again, we have our axes. And as kind of showed a little bit earlier, you don't have to draw these on the axes. And actually, I think a lot of times in physics, they don't necessarily draw them on the axes. I've seen people do videos that way, and sometimes in my classes, they didn't do it that way. But to be honest, it drives me nuts. I find it a lot easier to put an axis there. So let's say we have this line going from 0, 4 to, what did I make this one? 2, 0. So let's say that we have this line here, and technically this is a line, so it just keeps on going on forever. And we want to rotate this about the y-axis. Once again, the same idea. If we find the area here, rotate it around the y-axis, we can see that that would give us a cone this time. And yep, use a little bit of imagination. Still trying to get the hang of drawing on a tablet. So the other side would be right there. Now if we take this and we slice it into these thin slices like this, which once again would be circles, because the base of this would be a circle, because all I'm doing is rotating it precisely in a circular fashion. We're going to end up with all these little circles going down the y-axis here, and the equation for our line, which can be pretty easily figured out from what I have here, would be y equals negative 2x plus 4. And once again, we're going to use the same idea. Normally, when your sum is moving along the y-axis, you normally use the letters c and d. It really doesn't matter. It's just convention. So we're going to use the integral from c to d of the area, in this case with respect to y, dy. So what am I missing? So we're going to be finding all of these little areas. Like here's a circle that has an area, and then we're going to multiply it by dy, the tiny little thickness, to turn it into volume. Then we're going to add the next one. So let me kind of draw out what's happening here. Let's say we have this cone, because this is very similar to what we were doing with areas. I imagine you could probably use Riemann sums in the same way. I don't know, but yeah, I think you should be able to. It makes sense in my head. So let's say we have this cone. And if we wanted to estimate the volume of this cone, we could take, and let's say we already know the formula for the area of a circle, or for the volume of a cylinder, which is the area of a circle times height. We could take and turn this into a little cylinder like this, and calculate for this volume, then calculate for this volume, calculate for this volume, and so on. Maybe I'll finish drawing all of them. I'm not sure if I put too many lines on here visually, it just kind of turns into a mess. You can see you're kind of getting a shape. What's that thing called? I think it's called a ziggurat. Ancient temple kind of thing. You're kind of getting this shape, right? And if you were to calculate the volumes for each one of these shapes, which you would know how to do because you could measure the area at each point, like, you know, assuming you can get a ruler into this blob of whatever, you could sum all these up and that would be an approximation for the volume. And just like with the areas we saw earlier, the thinner you make these slices, the closer your approximation is going to be. If we make them infinitesimally thin and add up an infinite amount of them, it will give you the exact volume, which is basically what we're doing over here. So in this one, we have c to d. So we're going from our lowest point on the y, which is 0, to our highest point, which is 4. So we would have the integral from 0 to 4. Area, again, is going to be based off the formula pi r squared, where in this case r, as you can see, is our x value. Our x value at every point. So it's going to be pi x squared. Let's just write this over here. Area with respect to y equals pi r squared, which equals pi x squared. So we want to turn this into a formula. What do I want to say? We want to solve for x instead of for y. So we have y minus 4 divided by negative 2. So x equals y minus 4 divided by negative 2. So we're going to have pi times y minus 4 divided by negative 2 squared. That's our formula for our area. Yes, and that's what I had last time. So pi, which I could write the pi here, or I could move it to the outside. I prefer to write it on the outside. So pi y minus 4 over top of negative 2 squared dy. And once again, because I'm not trying to go over how to actually solve them, I'm just going to try to show what they are. We'll put this into the calculator. And we're going from 0 to 4. 0 to 4 of y minus 4. It was y minus 4 divided by negative 2 and square all of that. So this should be our solution. 16 pi over 3. 16 pi over 3. And then of course it's volume, it's units cubed. Whatever our units are, I didn't pick any. So this is how you can, another application of integration. What did I have here? I had another example. Okay, so for this other example, I want to keep this same line. We had y equals negative 2x plus 4, but build it into a different shape and see how that affects the setup of the integral. So, okay, I need my pencil. So we have the same line. I'm only going to draw the segment, but it's technically a line. This is 0, 4. This is 2, 0. And this is y equals negative 2x plus 4. And let's think, how did I do this? So for this one, what I want to do is say we have a shape. So in this case, I want this to be, I'm going to use the traditional 3D coordinates. So in this was x and this was y. Over here we're going to have this is x positive, this is y positive, and this is z positive. And so we had positive 2 on the x-axis. So that would be 2, 0, 0, because 0 on the z as well. And on the y-axis, we're going to go 0, 4. Let's say that's about here. So we have 0 on the x, 4 on the y, 0 on the z. This is the line, same line that I have drawn right here. But now let's say we want to build a shape by, instead of rotating in a circle as I did last time, which I rotated it around x-axis, so in this picture that would be rotating it this way. I can draw the picture. That would be rotating it like this and building a cone. But let's say I don't want to do that. Let's say I want to build squares. This is going to be hard to sketch accurate, but so for every point, I want it to be a square shape. So okay, well it's gonna end up looking something like this. And so in this case, let's say I have this shape, which I really didn't draw that well. It's kind of, it should end up looking like this is a straight line, this is a straight line, this is a curve that kind of curves outward and upward. I think this should also be a curve that curves outward and upward. And this is a straight line, something kind of like that. Straight line, straight line. Once again, this is a curve kind of shape. No, this should be a straight line. This one's a straight line. So the base is straight lines, shape, whatever. I think you say a regular shape maybe. This base back here should be a regular shape, but this is not. This top of it kind of goes like this. And the sides, I think the sides it's straight on the bottom, but no, it should be straight on the top as well. Anyway, I didn't draw it all that well, but just conceptually what I described before is each one of these is a square. So if we had that shape, or if we wanted to make that shape, we could do the same kind of thing. We could use an integral. And in this case, we're going to be doing the same thing. The way I sketched it out, we're drawing these squares along the x-axis. So they're starting down here, and they're moving in this direction. Sorry, along the y-axis. Along the y-axis. And the area of each one of those squares, so we're going to do the generic way we're going to set it up is the same as last time. Whoops. Actually, I like the color better. The integral from c to d of the area with respect to y dy. In this case, area with respect to y, our area of these squares, is going to be, so this is the x value, should be the x value times 2 and then squared. I think that's, yeah. So the area is going to be the length squared, and the length is 2 times the x value. So area with respect to y equals length squared. It's whatever the length of this base is squared, and these are supposed to be squares. It was designed that way, that these are squares. That's how I intended for the shape to be created. So the length, as you can kind of see, is going to be whatever this x value is times 2, because you have the x value going this way, and then that same value going in the opposite direction. 2x squared. So now this actually tells us the area with respect to x, and to get this to the area with respect to y, once again this is going to be x equals y minus 4 divided by negative 2. So we're going to have 2 times y minus 4 divided by negative 2 squared. So this whole thing is the area with respect to y. C and D are starting in the same spots as last time. We're going from y equals 0 to y equals 4, which can be seen over here, y equals 0 to y equals 4. So we have the integral from 0 to 4 of 2 times y minus 4 over negative 2 squared. This should give us the volume of this new shape right here that I created, which is kind of like a pyramid. It's almost like a pyramid. It's kind of a really funny shape. So integral from 0 to 4. We don't need, oh, I used x last time. I wonder if that actually gave me the right answer. It converted it to x when it solved it. That's okay. I should have used a dy, not dx. Alright, so the integral from 0 to 4 of, we need to put parentheses in here. I think I can do it like this. Yeah. 2 times y minus 4 over negative 2, the whole thing squared, and dy. So should be 64 over 3. So our solution is 64 over 3, which as decimal was 21 1/3. So about 21.3. So this is the volume of this shape. Alright, so that was another application of how you can set up an integral And you'll notice, hopefully, the common theme here is that you're adding up thin slices, basically. That's the common theme. All right, what do I have next as my example? I did that one. This one. So this is another one of the rotational volumes. Let's see how much of this I want to do. I'll just do this one really quick. So we have x, y. We have some curve here which I called y equals x squared. And let's go from the point where x is 0, which happens to be the point 0, 0, and y is 1, which happens to be the point 1, 1. And let's say we're going to rotate it this way around the y-axis, and that would give us this kind of shape right here. So we would figure out this volume right here. Another way that we could do this, and this one I'll even just set up maybe, and I just won't even throw it into the calculator because by now I think that if you want to see, you can do that yourself. So we have area should be dy, I think. Yeah, I don't know why I put should be we're going dy again because as we make these slices we're figuring up the slices in this fashion. So as we add them, we're moving along the y-axis. So area equals the integral from 0 to 1. As you can see, these are circles, so it's pi r squared, and r in this case is the x value, so it should be y equals, so it should be x squared, but it's going to be squared, so it should be pi x to the fourth, x to the fourth dx. Does that sound right? dy. No, that's why I need it to be dy. It should be square root of y x equals, is actually plus or minus. I don't think that matters. No, because we're going to square it. So it should be, this part was not correct, pi times x dy, x squared dy, where x is square root of y. So it becomes the integral from 0 to 1 of pi times y dy. That should be correct. Not sure what I have going on my notes here. I think that was for the other one. This should be correct. So if you were to solve this, this should be the correct answer. The other thing that you can do is starting with the same shape, x, y, and we're going with y equals x squared. We'll do the same points. We had 0, 0, and we had 1, 1. But we can rotate the same thing around the x-axis. And I think you can see when that happens, we're going to end up with more like a tornado shape instead of, this was more like a nice bowl shape, except it's solid. This is kind of like a tornado shape, or like a top maybe. It goes like that. We're going to do our slices along the x-axis like this. So we're going to want dx. Our formula for area is going to be, once again, pi r squared, because they're circles, which is just kind of given in the setup of the problem. And we need to take the integral from a to b, the first x value to the last x value. R in this case, as you can see, the radius of each of these circles is going to be whatever the y value is at that current point. So this one will be x squared. So this should be the integral from 0 to 1, 0 to 1 of pi x squared squared, which is x to the fourth, dx. So this should give us the volume of this shape that's going to look something like that. Almost like a golf tee. And then this formula on the left here should give us the volume of this shape that looks something like this. So, assuming that I didn't make any mistakes there, that's the setup. I don't think I did. My notes say something different, but I think my notes are actually wrong. Oh, I know why my notes say something different. I was actually going over something different. So let's take these same things, but do something. There's something a little bit different that I was going to do. Once again, I'll try to be quick about it, and probably won't even solve with a calculator. I already showed that that's possible. And all right, so going back to almost the same shape, except I didn't realize I had a second line drawn in. That's why my notes said something different. Oops. All right, so let's say we have this. Once again, it's x and y. And I do want the first line that I had. But I also want a second line. So this first line is y equals x. And the second line, which technically does keep going. I'm just not going to draw the rest of it because I actually only want part of it anyway. The same for this line, which also keeps going, but I don't want the whole thing, so I'm not going to draw the other half. This is y equals x. And if you, oh sorry, this one's y equals x squared. This one's y equals x. And it goes from 0, 0 to 1, 1. 0, 0 to 1, 1. And as before, we're going to rotate around the y-axis. So the area that we're going to be figuring out is going to look kind of like this. And if I try to sketch it, it's gonna look, it's gonna have this, oops, wait, let me try that again. The inner part will sort of look like this, and then the outer part will look like this, and except it's going to be that shape rotated all the way around. So it'll be like a shape, I don't know why I can't really sketch that very well, but hopefully that gives a sense enough of what it's going to look like. The outer side will be this smooth curve, and the inner side will be this flat shape. And to set this one up, it's basically the same as last time, except we have the one, just like with finding the area between two curves, when we're finding kind of like this volume between two curves, you take the one minus the other. And this one should be, yeah, the integral from 0 to 1 of, it's going to be pi r squared. R is going to be this one minus this one. So when you solve these for x, it's going to be square root of y will go in here. So it's the outermost one, which is this line here, which would be represented by square root of y, x equals square root of y. Minus the inner one, which is represented by the value y dy. Because in this case, what we're adding up is actually this little volume right here, which if I were to try to sketch that out, it could look like this side's flat, this side's curved, this side's flat, this side's curved, but it's three-dimensional. Kind of like that. Hopefully that was clear enough. This is why this is called the washer methods, because the little slices end up looking like washers. So this integral gives you these slices moving in this direction to find this volume. Once again, you could do the same thing with the same two lines. I'm not going to label everything, it's the exact same stuff as on the left hand side here. But you could rotate it this direction, and these slices, so this time now the outer edge should be flat. This was y equals x. The outer edges will be flat, inner edges will be these curved shapes like this, and it's like a cone shape, like that. I don't know, hopefully that kind of gives a little bit of an idea of what it looks like. It's not a very good picture, it's hard to sketch that. And the washers that we're forming are kind of the same. It'll have a curved shape on the inside, it'll have a flat shape on the outside. It forms this kind of radius shape like this like washer shape right there. And this one would be, where did I put it at? It should be this one right here. Yeah, so we have the integral. This time our slices are moving this direction along the x-axis, but it is still going from 0 to 1. Pi times x, the one that's most, the uppermost one, which is y equals x. So it's just x, but then we have to square it, minus this one, the innermost one, which is x squared, but we have to square it, so it's x to the fourth. X to the fourth dx. So solving this integral would give you the volume of this shape. And what's next? Arc length. I also touched on this a little bit in one of my other videos. I actually might have to split this into 2 videos. I was gonna try really hard to make it 1 video, but to be honest, it's just taking forever and I still have quite a bit I wanted to go over. Alright, well I think I'll stop with the next little thing that I'm gonna do, and then we'll go ahead and stop right here, I guess. I'll make a second video.